Very good. So let us now apply our Bohr-Sommerfeld quantization condition to the case of the hydrogen atom. So for the hydrogen atom, remember the key things that we have in mind then are, of course, this picture where we have our proton sitting in the center with our electron on the outside, going around, say, in some kind of a circular orbit. The idea here in this quantization technique is sometimes called semi-classical quantization. It's semi-classical because you think about the classical motion, but then you apply this additional quantization condition from Bohr and Sommerfeld. Now, as you know how to analyze a typical orbit like this, the key variables to consider are the radius, and generally we think a lot about the momentum going around the orbit. And so let's evaluate then, in terms of these key quantities, the Bohr-Sommerfeld condition. And then once we have the condition specified for our particular problem, we will then go on to use additional classical mechanics to finally solve for what allowed energies are consistent with our Bohr-Sommerfeld condition. Very good. So to evaluate the Bohr-Sommerfeld condition, we are saying that n times h must equal this integral. So I've got the integral around one complete cycle or orbit, taking the particle all the way back to itself. Then I've got the momentum times the distance. Now, as we know, if we have a simple orbit, a nice simple circular orbit like this, the momentum, which really should always be perpendicular to the radius, I think I've somewhat drawn it that way. The circle is a little lopsided. Nonetheless, as it goes around with that momentum, the momentum is constant, so I can easily pull that out of my integral. So I'll have the momentum times going around one complete cycle, the total path length. And that total path length then, for a circle, is simply 2 pi r. So now we can rewrite this condition. Let's think about the dynamical variables on one side of the equation, momentum times the radius. That would have to equal n times h. But then, of course, I'm dividing both sides by 2 pi to get the product pr. When I divide by 2 pi, of course, what comes out very nicely is my Planck's constant with the h bar, which usually is what comes up in more theoretical analyses. Okay, so that's good. That's the direct formal way to apply this principle. Now, I realize we've written the principle in a fairly formal form, so I'd like to just give a more basic argument, but you will see it will very quickly come down to the same value. So this is sort of, version 2 of the same kind of a thing. And this is sort of the more informal. And I just want you to see that they really are equivalent because this is the first time we're using this condition. So in this version number 2, the picture is, well, once again, I've got this electron going around its orbit. And as it does that with a given momentum, there's a wavelength associated with it. And all I'm saying is that I want this wave, when I get back to my starting point, to come perfectly back to itself. After all, if I go one full circle around, I'm coming back to the same point, so the wave should come back to exactly the same value. Also, we don't want the wavelength to be too long or too short because, as we said then, we'd get all this cancellation of the amplitudes as we keep superposing going around that orbit. So in this case, all we're really saying is that I want n times lambda, n times my wavelength, to equal the distance going around the circle, right? Where in both of these cases, we're of course saying that we want some integer number of these waves for n. So now, continuing on with this analysis, we know how to write lambda in terms of our quantum mechanics. That's h divided by the momentum. And now, again, we can solve for p times r. And when we bring p onto both sides of the equation, like so, it comes up here on top. And then on the right-hand side, I'll have n times h. And once again, let's clear both sides by dividing by 2 pi, which will then just give me, once again, n times h bar. So this is really just a little aside. It's fairly simple, but I hope you can see really the connections and how this simple physical picture really is equivalent to the more formal statement of the quantization condition.